All right, so this first chapter says units and measurements. Okay, so let's see what this thing is about. It's really giving you, it's an appetizer for the course, okay? So really just telling you about physics, okay? All right, so the question is, what do the laws of physics apply to? What do laws of physics apply to? What's that? Everything. Okay? It applies to biology, chemistry, everything. Okay? Why do we study biology? Because you can't study from physics and get to biology. It gets laws of physics are, very simplistic. To derive the laws of biology from the laws of physics would be too hard. So you study physics, biology, chemistry, and all. But physics laws apply to everything. Okay. Okay. It applies from atoms to rest of nature and galaxies and stuff like that. Everything interacts with everything else in the universe. Yeah. Do you know how many different ways things can interact?
A lot.
I'm sorry?
A lot.
Okay. At the fundamental level, there's only 4 ways you can interact. Okay? The strong force, the weak force, the gravitational force, and the electromagnetic force. And in everyday life, you really experience only 2 of those forces. Gravitational force, the earth is pulling you down, and the electromagnetic force is preventing you from going inside the earth. Yeah. So you really don't experience the strong and the weak force. Why don't you experience the strong and the weak force?
The atmosphere.
I'm sorry?
The atmosphere. The atoms interact with each other.
I'm sorry. Yeah.
It's because it's on a subatomic level.
Very good. The range of the strong force is about 10 to the minus 15 meters. You have to be that close. The range of the weak force is 10 to the minus 18 meters. You got to get that close to feel that force. Okay. This is the size of a nucleus. So you go inside a nucleus and you can feel the strong force. Yeah. So there's only 4 forces, and of those forces, you only experience 2 of those forces. Yeah. All right, so the laws of physics, it explains everything in nature, but there's a simplicity to them, okay? All right, so we'll dwell on this sheet a little. Again, this is just a fun chapter. This is just giving you an appetizer for what's coming. Okay? We'll talk about these pictures. Okay? We'll just show you the scale over which this is, the laws of physics apply. Okay? So what is this? What do you think this is?
It's gold.
It's So it's just a picture of a layer of atoms. Okay. You guys all know what an atom is. Here's I'm just going to draw a simple atom. What atom is this? Helium. Okay. So this is the size of an atom. What is the size of an atom? So it's about 10 to the minus 10 meters. Okay. The size of a nucleus is 10 to the minus 15 meters. Okay. So this is not drawn to scale. This is so for instance, if you wanted a scale picture, if if the atom was the size of a football stadium, the nucleus would be the size of a marble. So the atom is 100,000 times bigger than the nucleus. Okay. And like we said a minute ago, if you wanted to feel the strong force, you got to go in here. Okay. All right, so these are pictures of an atom. Pictures of an atom. And we'll tell you what these pictures mean. Okay. So this is a scanning tunneling microscope image. Anybody know what that is? All right, so here's what this is. Okay, so we're going to take a picture of this stuff, okay? And this is really, so I'm just going to draw a little picture. Those are bumps, like that. Okay, so how do we get a picture of this? So here's what we'll do. We'll take an electrode. Okay, so an electrode like this. And what we'll do is we'll connect, again, I'm just giving you a rough idea of this. Okay. We'll connect about 25,000 volts between there. Okay. And then what we're going to do is we're going to scan the surface. Okay. So we're going to move this and we're going to maintain a steady height. Okay. We've applied 25,000 volts. When the gap is small, what happens is electrons from here will tunnel there. Okay. And when the gap is small, more electrons will tunnel. When the electrode is over here, so the gap is larger and the number of electrons tunneling is smaller. So what you're doing is you're scanning this surface, and what are you measuring? I'm sorry? You're measuring the current flowing. Current is proxy for the height. Okay? So the bumps are larger current. Okay? So that's what you're measuring. Scanning, tunneling, microscope. All right? So that's what that is. So what is the size of this object that you measured? Oh, very good. Thank you, my friend. And that's the size of these guys. These guys are phytoplanktons. This is what these guys, what do their guys do? This is at the base of your energy pyramid. These are the guys that are trapping sunlight for you. Yeah. These guys are roughly the size of 10 to the minus 6 meters. Okay, so they range in size from 10 to the minus 6 meters to 10 to the minus 3 meters. A millimeter is 10 to the minus 3 meters. Yeah. So that's what these guys are. And you got to thank these guys. You know. They trap the energy, and eventually when they get buried, they become oil and all that stuff. These are two galaxies colliding. Okay. The size is 10 to the 16 meters. So you see, we're talking about stuff from 10 to the minus, in these pictures, from 10 to the minus 10 meters to 10 to the 16 meters. That's 26 orders of magnitude. Okay. This guy is 1,000 trillion times bigger than this guy. And physics laws apply to everything. Here's an interesting fact. Okay. There are many physical quantities we measure. Okay. velocity, forces. I mean, that's what you'll study in this semester. Velocities, forces, acceleration, intensity, and all the things you measure in biology and stuff like that. Okay? Every quantity you study in science can be expressed in terms of these 7 basic quantities. Everything you study. So to use a parallel, no matter what kind of house you build, these are the 7 kinds of bricks you use. Okay. Pretty amazing. And this semester, for 4 or 5 months, every quantity you study will be expressed in terms of these 3 quantities. That's all. These are the 3 bricks you'll use. So for instance, you'll study velocity. Velocity is distance over time, length over time. Okay. Forces are mass times acceleration. So mass times acceleration. Acceleration is length over time squared. Okay. So everything you study will be in terms of these 3 bricks. Okay. So here's a list of various quantities that are studied in science. So here's energy. Energy is the SI unit for energy is joules, denoted by J. And a joule is mass square, kilograms, meter square divided by time square. Okay. So we'll study forces, energy, power, and so on. Okay. So everything will be in terms of those 7 quantities. Okay. So scientists have agreed to have standard units for these quantities. Okay. So there's a standard SI unit for length is a meter, and we'll tell you what a meter is. The SI unit for mass is a kilogram. The SI unit for time is a second. Okay. So the unit for energy is a joule. Okay. All these units are named after scientists who worked in that area or made significant contributions in that area. Okay. So if you get your name on that list, you made it. All right. All right, let's talk a minute about prefixes. What do you think these are?
They go in front of the word.
I'm sorry?
They go in front of the rest of the words. They tell you the amount.
Yeah. So what is the SI unit for length? It's a meter. Okay. Okay, so if I tell you the distance to Jacksonville, okay, here's the distance to Jacksonville. I don't know, I just made that number up, okay? But it's roughly correct. You'll never remember this, okay? You're hardwired to remember small numbers, okay? This is not a good unit to measure the distance to Jacksonville. Okay. So how do we get a more appropriate unit to measure the distance to Jacksonville? What we'll do is we'll agree to apply a prefix to it. And 1 kilometer, this prefix is 10 to the power 3. Okay, and this prefix, so this is 10 to the power of 3 meters. And now the distance to Jacksonville is 96 kilometers. And even I can remember that. Okay. So you can use a prefix to a base SI unit to get a more appropriate unit for whatever it is that you do. Okay. So if you're into cell biology, cells are roughly the size of a micrometer, which is 10 to the minus 6 meters. Okay. So that's, if that's where you live, that's 10 to the minus 6. You're dealing with micrometers. If you're a nuclear physicist, what is the size of a nucleus? We just, very good, 10 to the negative 15 meters. And this is a femtometer. Again, so this is a femtometer. So this is equal to 1 FM. Okay. So anyway, that's what prefixes are. Prefixes are powers of 10, so you can derive appropriate units. All right. So now the SI unit for time is a second. Okay. Do you guys, do you guys know how we define our units of time? How did it all start? Okay. So the way it started was, what is the brightest object in our lives? This thing. Huh? The sun is the brightest object. So we decided everything. So there's the sun in the sky. There it is. Okay. What did we call that interval? So how long does the pizza need to be in the oven? Small. Right, the day into 24 hours. The hour is too long for the pizza. And then we have to have minutes, seconds.
So, I'm just curious, how is that number settled on as like what we're gonna define a cycle as? Like, why not a few cycles of the atom, more or less?
Well, so that was closest to the whole definition.
Okay,
We're defining it. So in some sense, it's arbitrary.
sure.
So if you can convince the entire world it's going to be 9 billion cycles, then that would be easy.
Right. No.
All right, so here's the question. The sun came back here, that's 24 hours. Does it take the same time every day? Why not?
Because we're orbiting, we're spinning, so it's shifting. Isn't it because the shape of the Earth isn't an exact sphere, it's,
Isn't it, because
Axis of
we're
itself.
turning on an axis while we're also rotating around the sun?
Is it because of location?
Our orbit is not exactly a circle. If it was a perfect circle, it's elliptical. All right. So here is the definition of the second. Okay. And why do we need this precise a definition? All right, you need it. And I'll give you an example why you need it. Okay. We do everything for a good reason in science. Okay? It's not arbitrary. Okay? Nowadays, you have these GPS devices that are absolutely amazing. You guys know how GPS works? You can be driving someplace, get directions, there's new construction going on, and it will tell you what lane to go. So the GPS can figure out your location within a meter. All right, the GPS is using electromagnetic waves. What is the speed of light? Okay, so the speed of light is denoted by c. It's 3 times 10 to the 8 meters per second. Okay, so distance is speed times time. Okay, so if you wanted 1 meter, okay, so a distance of 1 meter would be 3 times 10 to the 8 meters per second times 1/3 10 to the minus 8 seconds. Okay. 10 to the minus 9 second is a nanosecond. Okay. So if you wanted to determine your location to within 1 meters, you need to know you need to know the time to a nanosecond. Okay. So, and you're using it every day. Okay. I'm going to give you a very simple story. There's a lot of corrections to it. Okay. So, so here the Earth. So 12,000 miles above the Earth, surface of the Earth, there are GPS satellites going around the Earth. There's about 30 of those. Okay. And they're constantly sending out signals. Okay. And what these GPS satellites, this signal tells you the location of the satellite and the time at which the signal was sent. Okay. And your receiver gets the signal. Okay, so let's say here you are, and you get a signal from this satellite. So these are the satellites. And so you got the timestamp on the location of the satellite. So you are somewhere on this sphere. Okay, so here was the satellite it sent you, and you detect it, and you're somewhere on that sphere. But you want to know where you are. Okay. So now you get a signal from another satellite, and you are on the intersection of those two spheres. And the intersection of those two spheres is a circle. Okay, so imagine here's a basketball. That's the surface you're on from this satellite. And another basketball, the intersection of the two basketballs is a circle. You'll have to go think about it. Okay? You get a signal from a third satellite. The intersection of that circle and this circle, that sphere and this circle is 2 points. And then you need a signal from a fourth satellite to locate which point you are. Okay, so, well, again, go home and think about it. Okay, so you're getting a time signal from there. And then to calculate this distance within an accuracy of 1 meter, because your GPS does that, it tells you exactly what lane you're traveling on. Okay. To give you your location, you need to know this time of travel within a nanosecond. Okay. So you need to know your time very, very accurately for everyday life. Yeah. So that's why we are very particular about defining our units. Okay, so here, this is also a strange thing. You'll see why we define it like this, so I'll give you a reason for this. Okay. All right, so again, let's say we had defined, let's say our orbit was a perfect circle, and we defined our time using this phenomenon. What if you had a friend in another galaxy? How do you communicate the second to that friend? This is a very local definition.
Maybe use like the decays of something atomic.
Yeah, so you want a universal definition. And this definition that will give you everybody anywhere in the universe. All right, so let's see what this definition is. All right, so here's a nucleus, here's an atom. Okay, so these are the allowed levels. These are allowed orbitals. So in the ground state, all the electrons are in the lowest energy level. Okay, you can excite this atom. How do you excite this atom? I'm sorry? With a photon. Very good, my friend. So you can shine a photon on it, and this electron jumps from here to there. So there's an excited electron. And generally, it'll stay there about a trillionth of a second. And then this electron will fall back, and what will happen?
Release the same.
It'll release the same photon. Okay. The energy levels for every atom are unique. And each atom has how many different energy levels? I'm sorry? I'm sorry? Each atom has an infinite number of levels. And this is unique for every atom. So let's say you have atom A. When the electron jumps from here to there, it'll emit a photon here to there, you know. So the light coming from each atom is its fingerprint. Okay, that's what they use in forensic science. If you want to detect trace elements of stuff, just burn the heck out of it if you can burn it. Look at the light, and then you can identify what everything is. All right, so to define the second, we'll take a cesium atom. We'll look at one particular transition. Okay, and so when you get a bunch of photons together, now this is you get this they combine to give you a wave. This wave is coming at you. It's called an electromagnetic wave. Why is it called an electromagnetic wave? So it's called an electromagnetic wave because it has both electric and magnetic fields in it. So when you look at a beam of light, okay, so if the beam of light is traveling like this, and by the way, you use your right hand, if this is the direction of travel, your thumb points in the direction of the electric field, that's the direction of the magnetic field, and so on. Okay? So, and then the electric field is oscillating and the magnetic field is oscillating. So the electric field is oscillating like that. Okay, so in this beam, the beam is traveling in this direction, the electric field is oscillating in that plane, and the magnetic field is oscillating in this plane. All right, so so here, how are we defining the second? Okay, so we're looking at a specific radiation coming from cesium. Okay, so we're going to look at a specific radiation coming from cesium. We're going to stand here, and the electric field is oscillating like that. Okay, so the electric field is there now, it goes there, and then comes back. That's one oscillation. Okay. And we're going to count 9,192,631,770 oscillations. That's a second. It's a very precise definition, and everybody in the universe understands it. So there's a little thing in the statement. How does everybody in the universe understand it?
The seizing animal always give off that frequency of light when you're shining bright.
So we believe the laws of physics behave the same way everywhere in the universe. That's the assumption. Okay. All right. This is believed to be the smallest unit of time, the Planck time. Okay. Here's how the length was defined in the old days. Okay. So the shortest distance between the North Pole and the equator going through Paris. Okay. So 1/10,000,000th of that was a meter. Okay. This is assuming a flattening of the Earth of 1 to 134. 334. You guys go to that site and look it up, what the flattening means. Well, okay, I'll show you what the... Okay, so the Earth is not a perfect sphere, so it's an ellipsoid, and the flattening is defined as the semi-major axis minus the semi-minor axis divided by A. And that's 1 over 1/34. What that means is this is one part. If this was 334, that part would be 1. That's how much the Earth is flattened. Okay. Okay, so that's how meter was defined in the old days. Now since we have a precise definition. Okay, so we have a definition for the speed of light, and we know that we've defined the second precisely. You don't need any object. Again, your friend in a neighboring galaxy wouldn't understand this definition of the meter. He'll understand this definition of the meter. Okay, so the distance light travels in 1/300,000,000th of a second is a meter. Okay, and what is the assumption behind this? That light travels at the same speed everywhere in the universe. And I'm sorry?
And in every direction.
Yeah, and in every direction. So here's Planck's length. Okay. Here's a unit of mass, a kilogram. Okay. Now it's defined in terms of fundamental units, in terms of the Planck's constant, but this is something that was sitting in Paris. This is something that's sitting in Paris. That's a kilogram. Okay. And you can go to a store and buy kilograms. So ultimately, it was measured against that. Okay. What are all those bell jars doing? I'm sorry? You want to make sure that it doesn't react. If it oxidizes, it'll combine with oxygen and pick up mass and all that kind of stuff. Okay.
So, do we still define a kilogram as being related to that one object? We haven't found like some universal definition for it yet?
Oh, well, we have. So, yeah, your buddy in the next galaxy won't understand it. Here's something called the Planck's constant. Okay, it's joules per second. It's 6.67 times. So now the kilogram is defined in terms of this. So the Planck's constant, just like length was defined in terms of the speed of light, we take this is we say that this is Planck's constant. Just like when you defined the second, you said this many oscillations was a second. So this is the Planck's constant, and you can define the kg in terms of that, not in terms of any material.
Wouldn't this be a measure of force?
I'm sorry?
If it's meters squared, wait, no, it's not per kilogram.
Mhm. Yeah. Well, if it's per kilogram, then you take the inverse of that.
Yeah, exactly.
Mm-hmm. All right. All right, we want to understand this expression, order of magnitude. Mm. All right, so let's say somebody asks you, how many burgers are sold in Daytona Beach every day, for whatever reason? Yeah. Do you need the exact number or just ballpark number? Ballpark. Yeah. You don't care. It's if 894, it's roughly 1,000. Yeah. So it's roughly 1,000. This is known as the order of magnitude. Okay. So we want to know numbers up to a factor of 10. Okay. What is the order of magnitude of 1,000,000? 6. What is the population of the world? Very good. Roughly 10 orders of magnitude. Okay. All right, so that's what we want. This goes through calculating it accurately, but we won't do that. Okay, we won't. So order of magnitude of 800 is roughly equal to 1,000. Order of magnitude of that is 3. Okay. But if you wanted to do it accurately, you take the logarithm of that number. It's 2.9.
We don't see.
I'm sorry?
It is blank now, is that supposed to be? We'll see your laser pointer though. So it's not like the screen to turn off.
I don't know what's happened. When did it happen?
It's like maybe
Hmm?
a minute ago.
Oh, come on. Oh, there you go. All right, so if you wanted to calculate it accurately, take the log of that number, it's 2.903, and round it up to the nearest integer. Okay? But you guys understand what that means, okay? So again, the size of the visible universe is roughly 10 to the 27 meters. You saw that the size of an atom is 10 to the minus 10 meters, okay? And there's quite a few orders of magnitude that span those two quantities. Okay? Here are some interesting numbers. Okay, the size of an electron, the mass of an electron is about 10 to the minus 30 kgs. Okay. What is this? This is the size of visible matter. 10 to the minus 51 kg. It's 10 to the power of 51 kgs. Okay, you guys all know the composition of the universe, right? The universe is 25% dark matter, roughly, 70% dark energy, and 5% normal matter. What is dark matter? I'm sorry?
Do we know?
Yeah, we don't know. That's why we call it dark matter. And what is dark energy? We don't know what it is. That's why we call it dark energy. Okay? Blame it on the other thing. It's our ignorance, right? Yeah, this is normal stuff. So 95% of the universe we don't even understand. Okay, so this normal stuff, and this is about 10 to the 52 kgs. Okay, so here's an interesting number. Okay, that's the mass of the electron. So normal stuff, so here was the nucleus. Okay, so here's a picture of the atom. Where is the most of the mass of the atom? Nucleus. Okay. This thing, a proton weighs 2,000 times heavier than an electron. So all this stuff doesn't weigh anything. Okay. All the mass is there. And this is normal matter. So let's say 10 to the 52 kgs is this normal matter.
Writing again.
Yeah, nothing to write there.
It would show up at the moment you stop writing a number, it just disappeared.
Okay. Okay, I'll just hang out here for some reason. All right, so here's the normal matter, 10 to the 52 kgs, and the mass of a proton is roughly 10 to the 27 kgs, and I love this number. So what does this number tell you?
The number of protons.
Very good, my friend. Okay. By the way, the proton and the neutron weigh the same, so roughly. Okay, so 10 to the power of 79. That's 10 to the 80 protons in the universe.
That's a lot.
That's, well, yeah.
How do we know the mass of the universe? That you're dividing.
Well, that's a long story. Well, you count the number of stars, you know the mass of the sun, and that's another story. How do you know the mass of the sun? The point of this thing was there's beautiful numbers hidden in these little pictures. Okay. Do you know what Google means? I'm sorry?
10 to 100, right?
Very good. So this is Google. This is the number of protons. These guys are pretty modest, aren't they? So, okay, here the age of the universe, 13.78 billion years, okay, and so on. So here are some time measurements that we made. A year is about 10 to the 7, 300, okay, 30 million seconds, okay, and so on. All right, you'll need to do this in quite a few problems that we do. So for instance, here's a speed, 75 miles per hour. And what we normally do is we use SI units, so you really want the speed in meters per second. Okay? So here's the deal. So 1 mile is 1,600 meters. Okay, so a mile is 1,600 meters. So what is this fellow? What is this guy? I'm sorry? Exactly, that's unity. Okay, what is this guy? also 1. Okay, can I multiply phi by 1 without changing its value? Yep. Okay. So here is the speed. Multiplied it by unity. And I multiplied this by unity. So when you're converting units, all you're doing is multiplying by appropriate factors of unity. Okay? Of course, why did we multiply by this and not this? Because we wanted to cancel the miles, so you have meters, and cancel the hours. Okay? And 75 times that times this is this number. Okay? So 75 miles an hour is 33 meters per second. Why did we do this? I'm sorry? Yeah, we don't like to do Spanish, we like to do it in English. That's all. It's just a different language. Yeah. All right, so it's
How do you ensure that you're converting the numbers correctly? So or is that just comes with practice? You just know that going from miles
well,
to
what
meters
it
and so on.
depends on what your goal is. So you wanted to go from miles to meters, so you wanted to cancel the miles out, and the meter was in the numerator. The hours out, and you wanted the second in the denominator. Yeah. All right, so different units are just different languages, okay? Which is the faster speed? Yeah, they're the same, okay? All right, so here's something that you need to understand. In physics, all laws are expressed as equations, okay? So here's an equation, okay? And here's another equation, okay? Now, here's something that you need to understand about the equation. What is an equation? It's saying that this is equal to this. Okay. Now, can you have apples on this side and oranges on that side? No, then it wouldn't be an equation. So if it's an equation, if there is apples on this side, you'd have to have apples on that side. So if this quantity is measured in meters, this should come out in meters. Again, that's dimensional analysis. Okay. So what dimensional analysis will tell you is if this equation could be right. Okay. So let's say this has the same dimensions as that. How about now? Does this have the same dimension as that? Yes, it does. If you multiply by a constant, that doesn't change the dimensions. Okay? So dimensional analysis can tell you if an equation is right up to a factor of a constant. Okay? So let's see what's going on here. This is S is for distance. So the dimension of this is length. Is this equal to what's on the right hand side? Velocity, length over time squared, and that is time. Okay? So no, so this is so the right hand side has dimensions of L squared over time. Okay, so this equation is not right. Okay. So without knowing any physics, just you doing dimensional analysis, what can you do? You can eliminate the trillions and trillions of wrong equations. Okay, so that's what it does. Okay, so that's one of the first things you need to do. If you see an equation, you do dimensional analysis, or if you've done some kind of derivation, long derivation, you could check and see if dimensions are right on both sides of the equation. Okay? So for instance, so here is this equation. This happens to be the right equation, okay? So if you have apples on this side, this term had better be an apple, and this term had better be an apple. Because you can add apples and get apples. Okay. So let's do that. So S for this guy, the dimension, so the notation is as follows. So here's the equation. S is Vt plus 1/2 AT squared. So the dimension of S is denoted like that, which is L. And the dimension of Vt plus the dimension of 1/2 AT squared. The dimension of this is L over T times T plus A is acceleration, L over T squared times T squared. Okay, so this has L on this side, L plus L on the right hand side. So this equation is dimensionally correct. Well, so is this equation, S equal to Vt plus 10 AT squared. So, which one is the correct equation? All right, so that you have to find experimentally, and it turns out that this is the correct equation. Okay, so one of the first things you have to do is dimensional analysis, okay? And what is dimensional analysis doing? What does it do? All it does is verify that there are apples on the left-hand side and apples on the right-hand side. That's all. Yeah. Okay. Mr. Fermi was a famous scientist. He was a nuclear physicist. And he was famous for doing calculations in his head, ballpark calculations. Okay. So there is a famous story that when the first atom bomb was exploded, they were standing at a distance, of course, and you know, when you explode a bomb, you're interested in the yield of a bomb. Do you know what the yield of a bomb means?
The energy release.
Very good. Okay. And you know, we've dealt with TNT for a long time. So you measure the yield of a bomb in tons of TNT. So if it's a kiloton bomb, what that means is you explode 1,000 tons of TNT and the energy yield would be equal. Okay. A ton is 1,000 kgs, so 1,000,000 kg of TNT. A kiloton is. Okay. And nowadays, bombs are megatons and gigatons and stuff like that. And that's a lot of energy. So anyway, the story goes, so the first atom bomb exploded, and Mr. Fermi had taken a piece of paper and shredded into bits. And when the shock wave came, he tossed the paper. And from the distance the paper fell, in his head, he calculated the yield of the bomb to 3% accuracy. I don't know if you play golf or if you watch golf on, you know, these professionals will throw bits of grass, and from that they roughly have the idea of the wind speed. So, all right. All right, so we'll do a quick Fermi calculation, just so it's a quick and rough estimate. So I don't know. Let's do a problem. Okay, let's calculate how much water humanity drinks in a year. Okay. So I mean, you have to make assumptions. Again. We can say that each person drinks a liter. Hold up your bottle, please. That's a liter of water. That's a good estimate. Each person drinks that much water. How many people are there in the universe? Not in the world, in our world? 10 billion. Okay. How many days in a year? 365.
So 400.
Yeah, I mean, I can't multiply 365 in my head. Okay. 1 liter, so days per year, and 1 liter per day. Okay. So,
That first number, the number of people.
yeah.
Is Hero 400 down or up?
I'm sorry?
Is Hero 400 down or up? Because I saw something earlier that had like 465 rounded up to 1,000.
Yeah, no, I rounded 365 to 400. Okay, so 4 times 10 to the 12 liters per year. Is that an accurate number? No, I mean, it's ballpark number, but you didn't know about that 30 seconds ago. Yeah. And if you were Fermi, you would have known it in 2 seconds. And that's a Fermi calculation. Okay. All right, we want to understand significant figures. Okay. So, let's say I ask you to measure the width of this room. Okay. So let's say I gave you a meter stick and you roughly measured it up to how many meters? So you would say 25 meters. If you measured it to this accuracy, that's 10 centimeters, a tenth of a meter, you would tell me it's 25.6 meters. If you measured it to a centimeter, this accuracy, you'd give me 25.67 meters. If you measured it to this accuracy, that's a millimeter. All right, the significant figures on this thing are 2, 3 figures, 4, 5. Okay, so the number of significant figures reported in a number tells you how accurately you made a measure. Okay. All right, so there are, of course, rules associated with that, but how many significant figures are these? 2. Okay. So let's say you have $1,400, give or take $100. So you would write it as 1.4 times 10 to the 3. Okay, that's 2 significant figures. You have $1,400 in your pocket, give or take $10. That's 3 significant figures. You have $1,400 in your pocket, give or take $1. That's 4 significant figures. Okay. So if you want to convey how many significant figures you have to write it in scientific notation. All right, here's another thing that yeah. What we want to understand is precision and yeah. Okay. What? Okay, so we want to understand the difference between these 2 terms, precision and accuracy. Now you can have a very expensive piece of measuring equipment and it can measure precisely, but are you using it properly and measuring accurately? Okay, so let's say I want to measure the width of this table, and then I start off from here. I don't care how precise your instrument is, you're not measuring accurately. Okay? So here is a measurement that was done accurately, whatever. I mean, this is just to illustrate. So when you measure with accuracy, you will get readings close together. But you see, you're making a systematic error here. Okay, you're not measuring accurately, you're measuring precisely. Okay, here you're not measuring accurately, but you're measuring precisely. Okay. Now, of course, what you would want is both precision and accuracy. Okay, and then you can become rich and famous. Okay. All right, guys, we'll take a 5-minute break, and then I'll solve some problems.